Welcome to the last video in the Earth Science lecture series. Congratulations on all of your hard work. Hopefully your grades are fantastic and you've shown brilliance on all your assignments, and I want to thank you for taking this class. I hope you enjoyed this video series, and I hope that it's helped you succeed. 14 billion years ago, the universe came into existence. Using Einstein's theory of relativity and work, we know that energy would have been the precursor to the matter, and the matter would have moved from subatomic particles to hydrogen, large clouds, helium, stars, and so forth. And all this was set in motion some 14 billion years ago. Looking at stars, though, Hipparchus, we mentioned, was the first to classify a star's brightness. So we call the brightness of a star the magnitude, and there's two different types of magnitude we look at. We look at the apparent magnitude, which is how bright it appears to the naked eye on Earth, and the absolute magnitude, which we also call the luminosity. That's the amount of energies that is actually being radiated. The color of a star is determined by its temperature. We can measure the temperature of radiation and look at the wavelength and look at the color, and it all goes into the same black body experiment that we do in basic physics class, spectral analysis. The approximate temperatures for each color range are blue, white, yellow, orange, and red. You can see the spectral class given as well. This Hertzsprung-Russell diagram arranges stars by various properties. The sun, you can see the sun has a luminosity of 1. That's the index star, for instance, and we're yellow toward the bottom of the main sequence. The main sequence are also called dwarf stars, average stars, different spectral classes and different luminosities, different temperatures. You can read from the Hertzsprung-Russell diagram. We also have giants and supergiants. Supergiants are the huge massive stars, and upon death they become our black holes. Other stars like the white dwarfs are much smaller. So 90% of the stars or so are main sequence. So the sun is an average star, maybe on the lower end of temperature when it comes to stars. But by golly, it's a great star. It's my favorite. Stars, like I said, have life cycles depending on their size. You know, your average star winds up as a white dwarf after it goes through its life cycle, where a supermassive star could become a neutron star spinning really fast and emitting radiation, or the supermassive, the largest of the large, would form a black hole. So main sequence stars are the most common. That's the sun. We happen to be a yellow dwarf. Nuclear fusion is where the energy comes from. Giants and supergiants, the larger ones, the blue giants and the red giants. Blue giants are burning helium. Red giants are like Betelgeuse is a red giant, and its width is almost the size of Jupiter's orbit, so big. Supergiants then are the largest, the rarest, and when they die, they become the black holes. White dwarf then is a star made mostly of carbon toward the end of its life cycle. Remember, hydrogen to helium to larger elements. The brown dwarf is a star that's mass was too small because it's dead, but it's radiating heat still. And then the neutron star is a super dense star toward the end of its life cycle as well. Black dwarfs is that hypothetical star that would come from when the star was totally dead and had no more heat left. Of course, we don't know if they exist or not. It's believed that the universe is too young for a star to have fully died to be a black dwarf. And then black holes. Black holes are dead supergiant stars that collapsed on themselves and have intense gravity. Galaxies are systems of stars, trillions of stars, millions of light years of empty spaces between galaxies. So galaxies are star systems. The universe is mostly empty space. It's quite amazing. The elliptical galaxies are the oldest. They're the furthest away from the center of the universe. That confirms the expanding universe model. Hubble used the redshift and the blue shift to determine stars' motion, called the Doppler effect, the redshift and the blue shift, and found out that the universe was expanding, and the older galaxies toward the outside of that tend to be elliptical, very well organized galaxies. Spirals tend to be the majority of middle galaxies, spirals. We happen to be a barred spiral here in the Milky Way. So spirals. Have irregular galaxies. They could be young, they could be too small to have taken on a shape, but they're difficult to categorize, and they're irregularly shaped. Hubble, here's his tuning fork, which is how we classify galaxies, called the tuning fork system of galaxy classification. E stands for elliptical. Perfectly round is E0. Cigar shaped would be E5. S would be spiral. You could have a bar spiral or a non-barred spiral. And you just eyeball the galaxy and see which one it most looks like, and then you assign a number to it, a classification. The Milky Way, then, the Milky Way, that's our galaxy, is a large spiral, 400 billion other stars, and then our sun. So we have a lot of stars in the Milky Way. The Milky Way looks, and then we can only base it on evidence of other stars moving and nearby galaxies, because we've never really left the Milky Way and looked back on it. But you can see our sun up in the Orion arm, and then we are a spiral, semi-barred spiral, because the center's barred. We're 100 light years in diameter and 100,000 light years in diameter and 2,000 light years thick. So our local group, which is galaxies in the neighborhood, Andromeda is our sister galaxy. The Milky Way and Andromeda are on a collision course. Andromeda will cannibalize us probably because it's much larger. Triangulum's a little smaller. We have irregular galaxies, which we call the Magellanic Clouds, named after Magellan. And then other Messier objects. Last lecture we talked about Messier, who was an astronomer who loved comets and hated everything else, and categorized all of our local features. When you're talking solar system, you use astronomical units. When you're talking galaxies, you use the distance light years. Light years. About 10 trillion kilometers is a light year. That's the distance that light travels in a year. Now, I mentioned the Doppler effect, and I mentioned Hubble using the Doppler effect in the red shift and the blue shift to determine motion of stars. It is determined that stars are moving away from each other by using the redshift, and that supports the expanding universe theory. Parallax and triangulation, how we measure distance to stars within our galaxy. We can use Cepheids for really far away stars, but parallax and triangulation is how we measure stars within our area. Yeah, you can see we know the radius of Earth's orbit, and you can see how much the stars appear to shift in regards to our fixed sun, and then using geometry with a little trig mixed in, you can determine stellar distance. And I mentioned the Cepheid method for stellar distance as well. That's far stars.